Good morning class and welcome to our lectures in sustainable energy technology. Today we continue our discussion of how to store hydrogen effectively, and the first strategy we will discuss in some detail is storage through compression of hydrogen. As we discussed in the previous class, we can store hydrogen by compressing it at very high pressures up to from 400 to 800 bars. Okay. Now this compression process, as we showed, increases the energy density of hydrogen from around 10 to 11 megajoules to 3000 to 5000 megajoules per meter cube, depending on how large the compression pressure is. However, when you compress hydrogen, you need energy to compress it to such high pressures. So hydrogen compression in general requires around 10 to 20 megajoules per kg, okay, which can be a significant fraction of the energy released by the fuel. So if you compare, the total energy density of hydrogen is 120 megajoules per kg, and if you are compressing it to very high pressures, you can expend up to 20 megajoules per kg. So around 1/6 of the total energy content of hydrogen is expended through the compression process alone. If it's at lower compression, the energy required will be lower, but then also the energy density will be lower as well. So hence, while hydrogen compression increases the energy density of hydrogen, it decreases the round trip efficiency of hydrogen as energy storage material, because you are spending a lot of energy in storing that hydrogen. So that round trip energy density, how much energy you are getting back compared to how much energy you are putting in, is decreasing. You already have a efficiency due to loss due to electrolysis of electricity to split hydrogen into water. Then there is a energy loss due to compression, which further decreases the round trip efficiency. In general, isothermal, that is constant pressure compression, is more efficient than adiabatic, that is no heat loss compression processes. So if you see the two processes, this is the final pressure in megapascals. Now 1 megapascal is 10 bars, so 40 is 400 bars, 60 is 600 bars, 80 is 800 bars. And this is the compression energy as a percentage of the heating value of hydrogen. Alright, heating value is 120 megajoules per kg. So as we see, as the pressure increases, the compression energy increases, but it increases at different levels for different types of compression processes. For example, isothermal compression, that is, if you are compressing at a constant temperature, the energy loss is lower than 5%. Whereas if you are doing adiabatic compression, that is insulated compression processes, then the energy loss can exceed 15% and continues to increase as the pressure increases. Whereas isothermal, the energy loss increases rather slowly at higher pressures. Now, isothermal compression is difficult to achieve. So what is often done instead is what is called multi-stage compression with intercooling. You compress to a certain extent, remove the excess heat generated within the system so that the temperature drops back to standard temperature and pressure, and then you compress it again. So instead of a constant temperature case, what you will get is rise in temperature, then a cooling, fall, rise in temperature, then a cooling. And this way you can approximate the isothermal case to some extent. So this multi-stage compression process has better efficiency and hence it consumes lower energy. But still, if you are going to around 70 bars, you will lose around 10 to 12% of the heating value of hydrogen in the compression process. So in general, therefore, 8 to 12% of the energy of hydrogen is expended in the compression work. Okay. The other problem is hydrogen is an extremely light material and its atoms, hydrogen atoms, are extremely small. So it has a very high diffusion value. Diffusion means it is able to penetrate other materials very effectively because of its smallness. So hydrogen readily diffuses into the metal matrix of the containers, creating metal hydrides that make the metal weak and liable to leakage and loss of structural integrity. So the metal container is basically a matrix of metal atoms, and the hydrogen can readily diffuse to the interstitial spaces in this matrix and enter into the metal material, where it gets adsorbed into the metal matrix and creates metal hydrides, iron hydrides, aluminium hydrides, etc. Now these hydrides of course change the chemical composition of the metal matrix, making it less strong and more brittle and liable to cracks. Okay, so you can have a loss of structural integrity, which is very dangerous, especially if you are storing hydrogen at very high pressures. So the cylinder, if its tensile strength or ability to resist the pressure decreases because of the increased brittleness due to the formation of hydrides, then the cylinder can break and there can be a catastrophic explosion. Okay, you have heard of gas cylinder explosions of LPG. This is even more damaging. You can have because hydrogen is an extremely explosive gas when it mixes with air. So this weakening process is called hydrogen embrittlement and is a significant problem in the handling of hydrogen. This is very dangerous as hydrogen is highly flammable and an explosive material. To avoid such issues, polymer coatings are often used in the inner linings of hydrogen cylinders, which can act as barriers to hydrogen diffusion. There is a lot of research going on in developing better coatings that can further decrease this hydrogen embrittlement problem in the high pressure cylinders. Very high pressure H2 cylinders need to be thick walled to withstand the pressure. This increases the weight. Novel weight materials like carbon fiber have been used to decrease the weight and to avoid embrittlement problems. So what happens is, as you increase the pressure, the cylinder material also have to be thick enough to withstand that pressure, otherwise it will burst. Okay, but this increases the overall weight of the hydrogen storage system itself. Thick walled cylinders are definitely heavier than thin walled ones. So here metal cylinders are currently, there is research going on to replace metal based cylinders from and move to novel materials like carbon fiber based composites, which are light and tough, okay, and also will not have this hydrogen embrittlement problem. Okay, so carbon fiber based materials will have decreased weight and avoid embrittlement problems, and hence will decrease the weight and the durability of the compressed hydrogen. So hydrogen compression is currently the most well-known method and widely used method of hydrogen storage, despite its difficulties as we discussed, but there are other options also. A very mature technology is cryogenic liquefaction, which we discussed earlier. You are basically cooling the hydrogen to the point where it becomes a liquid instead of gas. The problem is you have to cool it to around 20 kelvins or at least below 33 kelvins if you are looking at high pressure systems. But if you are looking at a 1 atmosphere case, then you are looking at 20 kelvins, okay, which is an extremely low temperature. While the technology is mature because it was developed to create liquid hydrogen for rocket propulsion in space technologies, it is quite expensive and energy intensive. It requires currently around 50 megajoules per kg to cryogenically liquefy hydrogen. Remember, the energy content of hydrogen is 120 megajoules per kg. So around 40%, around 30 to 40% of that energy of hydrogen is being lost to cryogenic liquefaction itself, which makes it very difficult to make it commercially viable for energy applications. It is okay for space applications, but not commercially viable for energy applications at this stage. We can improve the technologies and decrease the energy content, energy required, and much work is going on regarding that. So what is being done here? A multi-stage cooling process requiring liquid nitrogen and chrome based materials that can withstand the cryogenic temperatures are required. So you need to first cool and liquefy nitrogen, and use the liquid nitrogen to cool hydrogen on the first stage. Then you do what is called a gas refrigeration system using a Brayton cycle to cool the hydrogen further till it liquefies. And further, you would need special expensive materials like chrome based materials that can withstand these cryogenic temperatures and still preserve structural stability and integrity. Because if something cools, it often becomes brittle, its structural ability changes. Okay. So you need a multi-stage cooling process involving liquid hydrogens and multi-stage gas-based refrigeration cycles and expensive chrome-based materials to store that liquid hydrogen. Further, you will have evaporation losses of 0.3 to 5% per day. So the liquid hydrogen, even if it's stored in very well insulated containers, will still suffer from significant evaporation losses per day, which makes it not viable for long-term storage systems. Okay. These are usually stored in double-walled stainless steel vessels with high vacuum between the walls to achieve insulation. So you have double-walled vessels and there is a lot of vacuum inside the walls to remove conduction and convection losses, and radiation will be minimal because hydrogen is extremely cold. Okay. So those processes, so cryogenic liquefaction is possible but very expensive. All right. Another option is adsorption in solid materials. As we discussed, hydrogen being a very small molecule readily diffuses into matrices of various materials where they react with the metal to produce hydrides. So instead of this, so this is a disadvantage when it looks at hydrogen embrittlement, but we can create specifically porous metal matrices with the express purpose that it absorbs a lot of hydrogen and create hydrides. Then you heat up this matrix at a later time to release this hydrogen. So this is called adsorption of hydrogen in solid materials. Hydrogen can diffuse and get absorbed in special metal matrices producing metal hydrides. If the metal matrix is heated, then the hydrogen gas is released back. It's a reasonably simple method of storing hydrogen at ambient conditions. So here you do not need a high pressure or extremely cold temperatures. You can do this in ambient conditions and you can just lightly heat it to generate hydrogen, which is also at ambient conditions. But metal matrices add to the weight and cannot store high volumes before reaching saturation. Okay. So metal matrices are again, you have to increase because metals are inherently heavy, it adds to the weight of the hydrogen storage and it cannot store large high volumes of hydrogen because you are still storing under normal conditions and you use the gases and the adsorption efficacy, it reaches saturation at some stage very quickly in short. So high volumes of hydrogen cannot be stored in this form. Okay. Another option is using chemical hydride. So this is basically physiabsorption where the hydrogen is getting diffusing and is getting bound to the metal matrix in a physical kind of a system to create metal hydrides. Okay. But you can actually have chemically bonded hydrides as well, which are much stronger and basically a different sort of chemical itself. Okay. So it's a stronger hydrides are formed. Certain types of metals can produce this. So storing hydrogen in the form of permanent chemical compounds like chemical hydrides. So these are called physical hydrides and these are called chemical hydrides. Chemical hydrides include lithium hydride, magnesium hydride, sodium hydride and sodium borohydride. And the hydrogen is recovered through catalyst activated hydrolysis of the form metal hydride to the power n. So how many hydrogen atoms are there with the hydride plus n moles of water to produce n moles of hydrogen and a metal hydroxide. So the metal hydride reacts with water under the presence of catalysts to generate hydrogen and metal hydroxides. Now the problem is you are not recovering the original metal, right? So so you need to do further processing to get back the original metal. Okay. Another is the catalyst can be expensive. So catalyst may be noble materials like platinum or other metals like ruthenium. Okay, platinum and ruthenium are common catalysts used for this chemical hydride decomposition to produce free hydrogen. The formed metal hydroxide has to be treated in order to get the original metal back so that hydrides can be reformed. So because you have to take this hydroxide out and create the original metal so that we can reform the hydrides. So this process also adds to the cost and complexity of the process. Okay. So this secondary extraction of metals back for regeneration adds to the cost and complexity of the process, but you are storing much more hydrogen in this form than just general physi-absorption of hydrogen. Okay. So these materials can store a lot more hydrogen at higher densities. Okay. A fourth option is ammonia-based compounds. So for ammonia is another option that you can use. So ammonia is basically NH3, and there is a very common process called Haber-Bosch process cycle where you can use nitrogen and hydrogen and generate ammonia. Okay. And the advantage of ammonia is it can be compressed and liquefied quite easily. In terms of its properties, it's almost like LPG. So you can have LPG cylinders, you can compress it and create liquefied ammonia under compressed conditions reasonably easily. So you can store it just like LPG cylinders, you can have liquid ammonia, compressed liquid ammonia cylinders. So ammonia under compression liquefies quite easily, so you can get liquefied ammonia gas, maybe something like that. Okay. Ammonia can be also converted to solid ammonia containing compounds like urea. So you have certainly heard of urea, it's a very common fertilizer. So you can, this ammonia can be further treated to produce solid urea, which is carbon monoxide and NH2 whole 2. Okay. Or metal amines like magnesium ammonium chloride, MgNH3 whole 6 Cl2, or ammonia borane, NH3BH3. Okay. So you can produce urea, you can produce metal amines, or you can produce ammonia borane, which are all solid hydrogen containing compounds. Okay. So you are basically transforming the hydrogen into a solid into a solid hydrogen containing compound. Okay. And ammonia compounds are one of the most efficient ways of hydrogen storage, but of course there are energy losses associated with energy needed to initially produce ammonia from hydrogen and later thermocatalytic decomposition of ammonia compounds to release that hydrogen. So first you have to produce ammonia from hydrogen and ammonia borane or metallamines, then you have to expend energy also to release that ammonia, that hydrogen back from that compound. So both of these steps also consumes energy, which reduces the round trip efficiency, but this ammonia and ammonia based compounds is one of the most efficient ways of storing hydrogen safely for long periods of time at reasonably good high energy densities, which we will see in the next plot. So here we are comparing the different types of hydrogen storage we just discussed. Okay. We are looking at two aspects: the volumetric density, the amount of hydrogen stored per meter cube of the storage material, the kgs of hydrogen stored per meter cube of storage material. So this is 40 kg of hydrogen stored per meter cube of material. This is 140 kg of hydrogen stored per meter cube of material. Okay. And on the y-axis, it's the energy content of hydrogen per kg of the material. Okay. So how much energy is available from the stored hydrogen per kg of the material which is storing it. Okay, megajoules of hydrogen per kg of storage material. They are not the same. For example, let us discuss a simple case. Suppose you have a 800 bar hydrogen in steel tank and 800 bar hydrogen in a composite tank which is made of carbon fibers, for example. Okay, both of them are storing the same volumetric density of hydrogen. So kg of hydrogen per meter cube of the storage material is the same. But because the storage material weight has decreased from steel to composite, the energy content per kg of material is greater. So per meter cube kg of hydrogen stored is the same because you are using the same state 800 bar compressed hydrogen, but because the storage material itself has become lighter, the energy stored per kg has increased. So 800 bar composite tank can store around 15 megajoules of hydrogen per kg of storage material, whereas 800 bar steel tank can store only 2 to 3 megajoules of hydrogen per kg of storage material. So you can see 5 times increase based on the new types of cylinder. So this kind of also shows the importance of research in improving the storage systems can have a significant impact on the viability of hydrogen as a storage medium or a production medium. Okay. What about other aspects? These are the metal hydrides, the physi-absorption methods. You can see the volumetric density is large. There is a catch. They can reach high saturation. Okay. So you can store per meter cube a large amount of hydrogen up to a certain point. Okay. So you can store around, you can go around 100 to 140 kg of hydrogen per meter cube of the material. So it's very good as a high storage material. Okay. You can store far more compared to a steel tank or a composite tank. Okay. In terms of meter cube. However, your energy density is similar to that of the steel tank case because metals are inherently heavier. So you're using a lot more metal. It's a complete metal matrix, right? So the weight is significantly higher. So the volumetric density improvement does not translate into an energy density per kg improvement. So it's still heavy. Okay. Here an improvement can be done if you look at lighter hydrides. Like the chemical hydrides that we discussed, this chemical hydride, sodium hydride, sodium borohydride, magnesium hydride, etc. These cases you have the same kind of volumetric density but much higher energy density because you are using lighter metals, lithium, sodium, magnesiums. Okay. But as we discussed, there will be problems regarding extracting it back. So there are energy losses here that needs to be considered, which we are not considering here. Okay. Liquid hydrogen has good volumetric density and extremely high energy density. Okay. You do not need a very thick cylinder or anything to store liquid hydrogen at 1 atmosphere. So the energy density per unit mass of the storage material is off the charts. It kind of goes up somewhere here. Okay. Then you have ammonia at 10 bar pressure. So you are pressurizing ammonia, but the pressure is much lower. It's not 800 bars, you can pressure it to 10 bars. So you are getting good specific energy density. The amount of energy stored in hydrogen molecule per kg of the storage material is higher than the 800 bar composite tank case. You are getting good volumetric storage density as well. Kg of hydrogen per meter cube is significantly high at this 10 bar pressure. So you are getting a very good overall system. There is methane. I have also shown liquid methane at 111 Kelvin. So cryogenic methane in this sense. Of course, methane is a non-renewable source of energy usually. It contains hydrogen molecules. So if this methane is suppose produced from CO2 sequestration. Okay, we will go there if we have time during this week. That carbon dioxide is coming from CO2 sequestration. It is reacting with hydrogen to produce methane. Then it is a sustainable way of generating methane. Then you can liquefy this methane at 111 kelvins and you get very high energy density of hydrogen. So just the hydrogen part of energy density is quite high. Volumetric energy density is also high. But forget methane for now. If you now look at the ammonium salts, ammonium borohydride, ammonium borane kind of salts, ammonia borane salts, these have the highest energy densities and the highest volumetric densities as well. So on per kg of energy stored basis and per meter cube of hydrogen stored basis, these are at the top right corner, so very high values either way. So they are very good and efficient ways. Ammonium salts are very good and efficient ways to store hydrogen. Okay. Ammonium boron hydrides. Okay. So this kind of gives us a snapshot of the storage. Compression is the best, is the most mature technology today. But it is relatively inefficient. Best efficient is the ammonium salts or light hydrides, which are increasingly becoming popular, as well as ammonia. Metal hydrides have a weight problem, so we need to move to light hydrides and ammonia boron salts. Okay. Now the next question is, how do we utilize the hydrogen? So we will just start today and we will continue in the next class. One of the best ways to utilize hydrogen is using what is called a fuel cell. So the latter part of this next few classes will deal with fuel cells extensively. So fuel cells are direct energy conversion devices that directly convert the chemical energy of the fuel, here hydrogen, into electricity. Okay. So you do not burn the fuel, you use the fuel and directly convert it into electricity. Okay. So does not use thermal energy as an intermediate energy mode and hence are not restricted to Carnot thermodynamic efficiency limits. Hence have much higher theoretical efficiency than heat engines. Because it is not converting it into thermal energy by combustion, the Carnot thermodynamic limits does not apply to it, and theoretical efficiencies are very high and practical efficiencies are also very good. Some other advantages: quick start and stop possible, as well as continuous operation. You can just stop the flow of fuel and it stops, unlike power plants that require a lot of effort to start and stop. Okay. Has no moving parts, obviously. There are no turbines, no compressors, no pumps, and hence is easy to install and maintain in that context. It typically works best with hydrogen. So it pairs well with hydrogen as the source of fuel. If a hydrocarbon is used, a fuel reformer is necessary to generate the hydrogen first, and then this hydrogen is fed into the fuel cell. So in a hydrogen based system, this problem is not, this disadvantage becomes an advantage, because it works best with hydrogen fuel cells. So you are getting good quality hydrogen, so you can use fuel cells to directly generate electricity as and when needed, which is very important for an energy storage system. Okay. Has no moving parts and hence easy to install and maintain. As we said, no turbines, no pumps, etc. Right? Disadvantage is it generates very low voltage. So it's similar to batteries. Actually, we will see that fuel cells are often like batteries, run in reverse. Okay. Typically about 1 volt, hence large power generation and delivery through fuel cell stacks is difficult. Because a single fuel cell can generate about 1 volt of potential gradient, you need large stacks to increase the the voltage, and then you can feed it to the main grid line as and when needed. Okay. So this provides a challenge. Okay. How to improve the voltage. Okay. So with this we will stop. We will discuss the fuel cell operating principle and different types in the next class. So thank you for listening and see you in the next class.